Okay, welcome to the second talk in the developer track. I'm very excited to welcome Kieran from Informatica, who's going to talk about exploiting GPUs for columnar data frames. Please help me welcome our speaker.
Hi, good afternoon, everyone. I'm honored to be talking here on the same stage as the founders of Scala and Spark. And so this is, so everyone in the morning has been talking about some love stories about Spark and Hadoop, Spark and Cassandra. So let me continue on the same theme. I'm going to talk on the love story of, or the emerging love story of Spark and GPUs. So this is the presentation link. I'm also going to display a QR code at the end of the presentation, so you can just take it off on your mobiles. About myself, I'm working as a staff engineer with Informatica. I spent quite some time in exploring new technologies, and I've also been spending quite some time looking at Spark and GPUs, and I thought Spark can benefit from GPUs. So a little bit about the company I work for. Informatica is known as the leader in data integration. We also have a number of products in big data space, and we obviously have a good enough interest in Spark. Informatica, a little bit more about Informatica. It was founded in '93, and since then it has seen a steady growth in revenue, customers, and of course employees. So the agenda for today's talk, we'll go through a brief introduction of GPUs, during which we'll also take a look at some of the existing big data applications which exploit GPUs already. Then we'll look at how CPU is the new bottleneck. It has been talked about again and again in the previous Spark conferences and also in the morning by Renault. We'll take a very brief look at what Project Tungsten does to solve it, and then we'll look at the current proposal of extending Project Tungsten to use GPUs in addition to CPUs. So basically, we'll look at extending in the compute direction for extending Project Tungsten. Then, as part of this, we'll look at the changes that are needed in Spark, which is code generation changes, batched execution, or columnar execution. And then, if time permits, we will have a demo. And we'll, of course, go through some of the future work that will be needed and some of the competing products of Spark, which can also leverage GPUs. So as we know, GPUs are omnipresent. We have GPUs present on compute devices ranging from smartphones, then tablets. You have some embedded devices like Jetson TK1 by NVIDIA, and of course the Raspberry Pi, which also has a tiny GPU. And then towards the other end of the spectrum, you have GPU-based servers, the server-class GPUs, which can have up to 5,760 cores on a single chip. And some of the leading cloud vendors providing pretty inexpensive GPU instances. This little graph shows the trend of GPUs versus CPUs over the past few years. And you can see that the blue line is the CPU trend, which is basically gigaflops computational capability, and this is GPU's computational capability. So let's look at the reasons how GPUs can deliver this. First of all, we have to, as we can see, the CPUs have like pretty powerful arithmetic logic units and large caches, and that is how they deliver the low latency computation, which means a serial task consisting of a set of instructions gets executed as fast as possible on a CPU. But as opposed to that, GPUs have much less powerful cores, but about 1/3 the clock speed. But they have a number of them. And although the GPU cores are less powerful and also smaller caches shared by a group of cores, GPUs can deliver a very high throughput. So basically, they are throughput devices. And the other aspect they can deliver a very high throughput is because of this paradigm called single instruction multiple thread, where threads are grouped for execution on GPUs. And a group of threads known as warps, usually the size is 32, they execute the same instruction. So the instruction fetch time from the RAM to the processor cache is reduced. And essentially because all the threads are executing the same instruction. So as they go through, and then the different threads in the group execute the same instruction, obviously on different data. Let's look at the programming model. There are two types of GPUs today in the market. Ones which are predominantly available today are the ones where they don't share anything with the CPU RAM. So for processing, you need to transfer data from CPU RAM to GPU RAM, transfer the compiled code to the GPU RAM, launch execution, and then wait CPU RAM, then the code on the CPU, where's the pointer? The code on the CPU waits for execution. So the second type of GPUs are the heterogeneous system architecture-based SoCs, where they share the RAM, and then there's no need to transfer data. And here is where the Java-based code, Java JVM-like code can benefit from such things, because you don't need to serialize your data to a different RAM. The code on the GPU can access all the Java objects, essentially strings and any other object, as long as it can determine the address of those. Next, we have the programming environments, or the IDEs. You have CUDA or C++ for NVIDIA GPUs. Then you have OpenCL, which is an open standard for all the GPUs. Both of these are based on, the syntax is essentially similar to C++, syntax, semantics, everything. And then you have the Java CL and the Scala CL as the native wrappers for these. And Aparapi is another library which converts your Java kernel code to the OpenCL code. And then finally, you have the JDK 1.9 lambdas, which can execute on the HSA-based GPUs. So next, we'll look at some of the examples in big data, in the world of big data. You have LHC CERN, which produces about 30 petabytes of data. They use their own big data software. It's a and they have some of the machine learning packages on GPUs. Then you have analytic databases specifically written for GPUs. They can crunch up to 2 terabytes of data to produce aggregations, 2 terabytes of aggregations per second, with the help of up to 60,000 cores on a single node. Then you have some deep learning applications where you have image classification, speech recognition, NLP, genomics. All of these fall into the realm of deep learning. And then finally, we have the a library called SparkCL, which was developed recently. It's an Aparapi-based Java APIs, using which you develop your RDD kernels using their APIs. And then this library, Aparapi, converts it into OpenCL. And what I'm proposing at this point is this is essentially a complementary approach, where instead of the developers writing code for GPUs, or even using the Spark CL APIs, the developers can essentially exploit GPUs if the underlying data frame code is changed. So that has, again, been the theme of the data frames, where the users get the benefit automatically. So this is a little bit of historical perspective. To wrap the introduction, you have Hadoop, which was based on co-location of storage and CPU. Spark came into picture with using RAM more efficiently. And then now we are extending this in the compute dimension, where we want to use not just the CPU, but any additional auxiliary hardware like GPUs, which are most likely present on servers. So this is a Spark. So let's begin with the proposal. This is the Spark SQL architecture, where the computation expressed in the form of SQL queries and data frames is converted into the logical plan, physical plan. We have all seen that. And then finally, it goes through, it's converted to a set of RDD APIs. So the data structures of interest for this talk are the tungsten row, and also a normal row, which is an array of Java objects, one object for each column, and then the columnar cache, which essentially represents, which essentially is a byte buffer per column, and each byte buffer contains data for each row. So again, we have all seen how CPU is the new bottleneck for Spark computations, and that's because of the much higher throughput given by the hardware advances in the last 5 years for network and storage. Then you also have some software advances in the form of Spark Optimizer, which minimizes unnecessary disk I/O. Then you have the more improved file formats getting popular over the older text-based file formats. And you also have a much better memory bandwidth compared to a few years back. But as we saw, the CPU hasn't improved that much, or it hasn't kept pace with the improvements on the I/O side and the memory side. So that is where we have more data available to process, much more data being dumped on the CPU, and the CPU is overwhelmed to process it at that speed. So that is where Project Tungsten came into picture. They introduced 3 elements, basically taking over the memory management, introducing new data structures for specific algorithms, and then finally the code generation, where the generated Java code is applied to each row instead of using an expression tree evaluation approach for evaluating expressions. So the current proposal is about changing the Java code-based execution to an execution targeted at GPU. So here, what we want to do is, instead of doing the serial row-by-row execution, we want to execute a bulk set of rows in parallel on GPU using the parallel, highly parallel architecture of GPUs. So what this entails is changing the code generation to generate Java CL code, change the executor code in the Tungsten project, and whichever ones which execute expressions to execute Java, the OpenCL code through Java CL. Then finally, the biggest change in terms of Spark architecture will come in the form of changing to columnar layout of execution rather than an execution on a per row basis. So what this means is we need to develop a few classes. Essentially, you need to develop batch row instead of an internal row class. And this batch row is quite similar to the cache batch, which has been present since the Shark days, which basically just maintains references to the columnar buffers. And then you need an unsafe column class, which is similar to the byte buffer class. And this unsafe column needs to be used instead of the unsafe row that was introduced in Tungsten. So before we get into the details, this is this is a small difference in the row-wise and the columnar storage, where the data represented here, in the row-wise format, it's stored like this, and in the columnar format, it's stored like this, where each column is stored contiguously in memory. All the rows for a column are stored contiguously, instead of all the columns of a data being stored contiguously. So let's look at the code generation changes needed for this. You have this apply function, which is the core of the pointer. OK, the pointer is gone. So the apply function here essentially does the execution. And this generated code's apply function is invoked on every row of the data in the partition. And it performs the computation by extracting individual columns of that row, input row, and then it produces the output as another column in the output row. So let's look at the GPU-based execution, where you have the same code executing in the columnar fashion on different cores of the GPU. So remember that this code is executing parallelly on a number of rows, hundreds or even thousands of rows at the same time. So it makes sense to actually execute, to actually just dump a number of rows on the GPU rather than executing one row at a time, which is the current case. So as you can see, the GPU code first extracts its own thread ID, and the thread ID is used as an index or the row ID for computation. And this kernel executing in the context of one thread does its own computation and gets out of the way. So the Scala code to drive this OpenCL code, this is what it needs to do. It needs to first iterate over a number of rows, build a set of byte buffers representing the input for this function, A, B, A nulls, and B nulls. These are the arrays which you need to pass. And then it transfers those byte buffers to the GPU RAM, launches execution of compute expression on the GPU, and then finally it reads the output and the out nulls arrays into the CPU side of byte buffers. And then this is what is transferred to the cache. So let's look at the row-wise execution, just as a comparison. So in the row-wise execution, the row is represented as a structure of fields in the row. And here, as you can see in the previous slide, the computation involves only the columns A and C. It does not involve. So here, the computation involves only the columns A and C. And B is not used. But still, it needs to be passed because it's a row-wise representation. So this data is represented in the CPU RAM like this. Then it's transferred to the GPU RAM as an array of structures. Then it's transferred. Then when the threads start executing, it executes from the GPU RAM, the data is transferred to the streaming multiprocessor cache. And then it uses the elements A0 and B0. So the thread T1 uses elements A0 and T0. Then when the thread T2 starts executing, the data is already there. And it uses A1 and C1. And as you can see, the elements B0 and B1 are not used at all, but they are still transferred from CPU RAM to the GPU RAM. And finally, when thread T3 starts executing, the data first needs to be transferred from GPU RAM to the CPU, the processor cache, and then it executes. Compare this with this columnar execution, where the data is represented like this. The first set of first the data for column A is transferred, and this is the corresponding code for the columnar execution. You can see that we are not passing the pointer B at all. Only the pointers A and C are being passed, and the computation is expressed as A and C. So the data for columns A and C is transferred. Then when the execution starts, thread T1 executes A0, it's there. Then when it requests C0, it requests the entire column C. When the second thread requests A1 and C1, it's already there. When the third thread requests A2 and C2, it's already there. So as you can see, the columnar representation minimizes the data transfer from CPU RAM to GPU RAM, and again, from GPU RAM to the processor cache. This can still be neglected if we had an array of structures like C has, where the elements in the structure and even the elements in the array are contiguously located. But in Java, you don't have members of a class contiguous in memory, and similarly, the array of Java objects is not contiguous in memory. So serialization is needed before you transfer to GPU RAM. Whereas in the columnar representation, you don't have any of those problems. It's already serialized. It saves the memory bandwidth, memory transfer bandwidth, and it also avoids copying of input data. So let's look at an example, a real example, which I used for testing all of this. So basically, you have, let's say you have an in-memory RDD being converted to a data frame. It has two columns, x and x square. And the place where I intend to change is basically in building the cache. So you have data.select. So the original data frame, on the original data frame, we are selecting the first two columns as they are, and then we are building a third column as an expression of the first two columns, and then finally caching it. So the data1.show is what triggers the execution. So in the row-by-row execution, the current format, you pass 1 to the closure, to the original closure here. Then you have which produces this row, and then executing the expression produces a result row, which in turn goes into the cache. So the build buffer function of the method of the columnar cache gets this data. Then similarly, you have data for the next row, and then basically the columnar cache is built as an array of columns, each column containing data for all the rows here. And when the result needs to be produced for this show, what happens is it takes data from the columnar cache and then produces and then builds the rows like this. So let's look at the proposed implementation. You have the same thing, but now we are executing the lambda in a vectorized fashion. So this lambda, instead of being passed just the first row, it is getting passed a bunch of rows, which produces a columnar output. And then on the GPU, so this columnar output is now easily transferable to the GPU. And the result of the GPU computation is essentially your cache. So, and then producing output is same as before. So as you can see, so even going through these slides took me less time than, so you can see that the execution will also take less time. So again, this can be done for all, not just for in-memory computation. So this is where your columnar cache building can benefit. So let's say this is a data pipeline consisting of some sources. You already have Parquet, ORC, and relational DBs through ODBC interface capable of delivering you the columnar inputs. So the ODBC, so JDBC doesn't support the columnar or the arrayed input, arrayed reading of result sets, but the ODBC interface does. So, and the Parquet and the ORC, you can already read a bulk rows for given columns. So that can be used straight away for converting in-memory RDDs. You essentially need to do, like, when you want to execute them, execute on an arrayed input, a given lambda function, you need to do some bytecode modification. And then the output can also be produced in a bulk fashion. And then this columnar cache building is where we have the benefit of building it much quicker than the previous case. So this is a result. So this is just a result, a partial result of computing an expression. So this this red line is for the CPU. It's a time in microseconds. And you can see that the computation time needed on the GPUs, this line goes up much smaller, much less quicker than the CPU line. And this computational time difference is accounting the fact that you have to convert data from row-wise into columnar and then transfer data and all that. So this GPU time, the blue line, includes the time to convert data and then getting the results back. So if we didn't have to do that, this line will, the GPU line will be essentially flatter. So let's just go through a roadmap for future changes to wind up this talk. For Spark, the next improvement can be in terms of multi-GPU, where where the same code can, so if a node has multiple GPUs, this Spark should be able to exploit that. Then you have some algorithm. So then you'll have to do hand coding changes. You'll have to essentially rewrite some of the algorithms for GPU, and those involve sorting, aggregations, union, and join. So these will have to be essentially rewritten for parallel, as a parallel implementation on GPU. Because there's no code generation like thing involved here. Then other projects capable of competing with Spark, which can also exploit GPUs efficiently, are Impala, which is the C++ code base, and it's easier to adopt for GPUs because you have contiguous arrays and all of that in C++. Then you have CERN root, which is actually, this CERN root is an interesting application because, like Spark, CERN root also has a ripple, shell-like ripple interface where you can execute C++ code line by line, and that's a very interesting application. And they already have multi-node execution capability. And given the fact that C++ 11 has lambdas, functional programming, I think this is also a very good use case for execution on GPUs. Then you have other things. And then this thrust and boost compute are two Scala collection, not Scala, the GPU collection libraries. And they gave a similar interface to the C++ STL interface, which is similar to Scala collections. And then you have VexCL, another library, and that's it from my side. I think we have 1 minute.
Yeah, I think we've got time for one question, if anyone has anything up in the back.
So while you're breaking out of the JVM anyway to obtain more performance, why not look at using our CPU properly? Because right now the JVM is yeah, it's what's keeping us back, because it's pretending our CPU is from the 80s and not using any SSE or anything like that. So if there are such gains even on the CPU, why skip that step and break out to GPU directly and not make a comparison on the CPU side?
I think GPUs is kind of auxiliary or complementary hardware that is present. It's much cheaper than, and it's much more power efficient than CPUs. So if you remember the graph on the slide that I showed, there are like a few more trends of GPUs that have emerged in the last 5 years. So in 2010 kind of time frame, the GPUs were not that powerful. They had like max about a few hundred cores. But today, the GPUs have like thousands of cores. And the power consumption per gigaflop is also pretty low compared to GPUs, compared to CPUs. So that is why the trend is towards moving to GPUs, because now you can have much smaller clusters. In fact, you may not even need a cluster if your data is not that big enough. And if you remember, I showed on the big data slide, there are a few GPU DBs specifically written for GPUs, multi-GPUs on the same node. They can process up to 400 terabytes of data. And the aggregations can scale to 2 terabytes per second. I don't think Spark matches that today.
OK, I'm sure Kieran will stick around if you have more questions. Please join me again in thanking our speaker. So we got like 2 minutes if you want to like set up and stuff.